My name is Dave. As Raphael mentioned earlier, I help maintain the WebGL part of the P5 library. I went to grad school to do computer graphics, and I spent a lot of time there working on computational geometry, dealing with digital sketches. So I've been spending a lot of time over the past few years thinking about lines. And today I'm going to talk about how to draw a line, which sounds like a simple topic, but you can go pretty deep into drawing lines, and specifically lines in generative art and how you can make your code for lines more expressive. So to start off with, I'm just going to take a step back and look at general art, not just computer art, with just like a few small examples of the variety of lines that you can have and how the style of line you pick, it's kind of load bearing in like determining the aesthetic of the work. So here we've got two pretty different styles of lines. On the left, we've got pretty geometric lines with a thin, rough, pencil-y texture, versus on the right, we have thicker, blobby, confident strokes, but with a wobbly, off-kilter style to them. And each brings something totally different to the table and it really changes the feel of the work. So this is a choice that as an artist you can make to influence what the end result is going to look like. But now if you're using P5 and you try to draw a line, you're going to get something that looks like this at first. Now this isn't bad. It's a pretty nice line. But the question is, do we have any choice here? Can we do anything differently if we want? So what I'm going to do today is I've got the P5 editor open here. I'm going to do some live coding. We're going to make some code that draws some lines, and we're going to go through some different techniques that you can use to try to change up your lines a bit. So because I'm live coding, there are going to be bugs. So if you notice a bug before I do, feel free to let me know in the chat. And if you're doing stuff on your own and run into bugs, just know that that is part of the process. It's going to happen. And we'll help you work through it. And you can help me work through it maybe. Okay, so before we get started with the coding part, let's get some input. So if we're going to talk about some lines, let's get some interesting lines to draw. So I'm going to start off by making a little line drawing app so that I can like click and drag to draw some shapes. And let's see how we're going to represent that in our code. Let me just go over to Paint here. So how do you represent a line in code? Well, for that one single line we had before, it's kind of like 2 points. And then we just connect the dots with a straight line. Now in the computer, we represent each one of these points as a coordinate on a graph. So we've got 2 axes, our x-axis and our y-axis, and each one of these points has an x and a y value, an x and a y. The x just kind of like corresponds to where it hits on this line, and the y corresponds to where it hits on this line. And in P5, the top left corner of the screen is 0, 0. So this is one line segment. And what I'd like to get overall is something where you can click and drag and make multiple strokes. And those are not straight line segments, those are curves. But something we can do is take a bunch of points that all move just a little bit at a time, and then connect the dots with straight lines. And although in this example, it looks a little bit rigid, if you have enough points in between, it will end up looking smooth and you won't be able to tell the difference. So we're actually just going to work with these like connect the dots data structures instead of actual curves. So then the question is, okay, where do we get these points from and how are we going to draw them on screen? So if we have multiple strokes, each one of these is their own set of points. So if I'm going to make a data structure for this, let me just bring up some a notepad so we can type. I'm going to store everything as, let's say, a variable called strokes, and that's going to be an array where each one of these guys is its own thing in the array. And each stroke is itself going to be an array because we have to store all of these different points. So we'll have 1 point, and then another point, and then another point. And then if we have multiple strokes, we might have multiple arrays. So in our drawing app, what I'm going to do is when I press the mouse down to start a new stroke at this point, we're going to go and put a new array into this strokes array that starts off with just the mouse coordinate. And then as you drag the mouse, let's say I drag the mouse over here and we start to connect those dots, we're going to go and add another point into this array. And as you drag the mouse again, we'll add yet another point. And so on and so forth. So I'm just kind of using a shorthand here for points with like this X, Y, and brackets. But in P5, if you want to make a point and store 2 coordinates, you use a function called create vector. And you give it an X and a Y. And then it will store those for you. So I think that's enough to begin getting started here. So like I said before, we're going to have a strokes array to store all of these points. And when we press the mouse down on the canvas, we want to add a new stroke. So in P5, there's a special function called mouse pressed that will get called whenever the mouse is pressed on canvas. And when that happens, we'll make a new stroke. And we're going to put the current mouse coordinate into that stroke. And so we'll create a vector. And there's some special variables in P5, mouse X and mouse Y, which store the current mouse coordinate. And then we'll add this new stroke to the list of all the strokes. So then when we drag the mouse, there's another special P5 function for that called mouse dragged. What we want to do is add the current mouse coordinate to the last stroke that we've been working on. So we'll just grab the last stroke. And then we're going to put the mouse coordinate into that again. So I can just copy and paste this from before. And that's all we have to do to create and update strokes. So now let's draw them. So P5 has some settings we can use to control the color of strokes. So I'm just going to say black for now. We don't want any fill. It's just going to be lines. And I'll try to make the strokes thicker so you can see them with the stroke weight. So now what we're going to do is loop through all of these strokes and draw each one in turn. And all of our strokes are connected dots. So we have to make sure that there's like at least 2 dots to connect. So the first thing we'll do is just double check that that's the case. So if we have less than 2, we'll just continue. But otherwise, so we're going to draw all the dots and have P5 connect them. And so there's a shortcut to do this in P5 called begin shape and end shape. And then in between these, we can call vertex with an X and a Y value as many times as we want. And P5 will connect the dots for us. So we're just going to loop through all the points in the stroke and do 1 vertex for each of them. So I think that should be enough to get us started. So let's see what happens. Cool, I can click and drag and make some strokes. So now we've got some input, and now we can start to work on making our lines look a little bit nicer. So the first thing we'll notice here is that this is just taking exactly my mouse as it comes in. So if my hand is a little bit shaky, my lines are a little bit shaky. We can do a bit of processing on the points that come in to try to change the feel of the line a bit. So one little trick that we can do to smooth the line is when you add a point and then you move the mouse over here, instead of directly adding that point to our stroke, you can add a point that's halfway between the last point and it. So then if I move the mouse down here, again, rather than jumping all the way down there, we'll add a point that's halfway there. And we can just keep doing that. And what you'll see happen is when the mouse moves up all the way here and down all the way here, the actual line that we draw only goes up a little bit and only goes down a little bit. And it minimizes the variation in the stroke. It's kind of like the last point in your stroke has some inertia and the mouse is just like dragging it towards it, but it doesn't jump immediately there. It kind of just moves a little bit of the way. So if we're going to do that in P5, this is going to happen in our mouse dragged thing here. And we're not going to put the mouse coordinate directly in. That's just going to be, let's say, our target. And so we've got this target point, and let's grab the last point so that we can go partway there. So we'll just grab the last thing out of the stroke. And what we'll push to the array is going to be something partway between. And in P5, there's a function called lerp, which stands for linearly interpolate, which means basically mix. So we're going to mix between the last point and the target point, and then we can give it a fraction. I'm going to put in, let's say like 0.1. So we're going to go 10% of the way just to really show the effect here. Oh, so I have accidentally modified the last point. So I'm just going to copy it first. There we go. So you can see now, as I draw a line, it kind of trails behind. So this is with 0.1. And just for reference, if I do like 0.9, so it goes 90% of the way, it follows much more quickly. So I'm going to bring it back down to 0.1 to get it really smooth. So if I wiggle my mouse a lot, the line ends up a lot smoother than it would have otherwise. And so that will help influence the style, make it a lot more curvy and precise looking. Cool. So next thing we can try to do is maybe change up the fact that this line has the same thickness the whole way through. So that's like one of the things, one of the knobs you can tweak in your drawing is like, instead of making each stroke have one character, you can like vary the character along the stroke. So what I'm going to do is, instead of storing the points directly, I'm going to start storing them as an object with multiple properties. So before we just had a point, but now each point is going to be an object, and it'll maybe have like a point property in it because we still need the position, and that'll still be like a create vector. But then we'll also put in, let's say, thickness. And that will just be a number like maybe 4, something like that. So when I put any put any point into a stroke, I'm now going to put in an object with a point property and a thickness. And when I drag the mouse, I'm going to put thickness that changes, so it won't just be one value. So here's the point from before. And then, okay, so let's pick a thickness that'll change. I'm going to maybe use a sine function for this. So I'm going to say like 10 plus 8 times sine of, let's say, the length of the stroke. So what this is doing, a sine function looks kind of like this. So if this is your input axis, and this is like the output, sine of x, it will look kind of like this. And so I am starting at like 10-ish. And then I'm putting a sine function on top of that. I'm adding to it. So we end up getting a sine function like that. And if you imagine 0 is like the middle of the stroke, and this is the thickness, it's kind of like we're putting this on either side of the stroke. So if I draw a line like this, the stroke will go like something kind of like that. So now to actually draw this, unfortunately, we can't use this begin shape, end shape thing, because in P5, you can't change the thickness up for a line in the same line. So instead, what we're going to do is just use this stroke weight function to draw multiple lines with different stroke weights. So I'm going to cut this from here and then loop over each pair of points that we can connect with a line. So I'm going to start from 1 so I can connect the previous one to the next one. So now I'm going to get the 2 points that I'm going to connect. And so we'll set the thickness now, and we'll grab that from the previous point. And now connect the dots with the line function. So we're going to go from the previous point to the next point. So if we draw that, oh, what have we got here? Yes, so the last point, I was before treating this like it was just a position, but now it's an object with multiple stuff. So I gotta get the position property out of it. So now we have varying thickness, but we have a bit of a problem, which is we've got like very obvious edges between the different stroke segments. And that's because the way that we're drawing the lines, we're just having like multiple straight lines, and then we're just changing the stroke thickness suddenly. So there's not a smooth transition. The different line ends just butt up against each other. So what we'd ideally like to do instead of doing this is something that looks a little bit more like this. So we're still building it out of straight line segments, but each segment is like a trapezoid so that the ends of each segment directly touch each other and there's not a sudden jump. So the question is like, how do we come up with this trapezoid shape from just our center line points? So we're going to do a little bit of math for that. Let's get a little example going. So let's say we have some points like this, and we want to connect them. So here's the center line. And maybe we want to connect them like this kind of. So I'll just draw our shell over the points. So it looks like we've taken each point and like extended it in two directions. And it's kind of a question of what direction do we extend each point in? So in order to talk about directions in code, we have to talk about how you would represent them. So I mentioned that points are a coordinate, an X and a Y. And a direction is also kind of a coordinate. So if we've got 2 points, I'll call this one A and this one B. If we want to talk about the direction between them, this would be B minus A. And what this is really doing is it's just taking the X coordinate of B, subtracting it from the X coordinate of A, and same with the Y coordinate. And even though I'm representing this one with an arrow, it's kind of also a dot. It's like sort of like a point right here. It's as if I'm taking this to be the 0, 0 point of the graph. And the end of the arrow is where that point would be if you put 0, 0 over where the coordinates have their 0, 0. So if this is how we get a direction between things, then I can get this direction between each pair of points. And then what we can do is rotate that 90 degrees so it's facing out. And then this direction looks like this is maybe around 90 degrees. This is reasonably close to the direction that I drew before. It's not like exactly how my drawing looked, but this is going to be our strategy for expanding these points because that's going to get us a pretty good shell. So we have to expand it in 2 directions, both the outside of the stroke and the inside. So what we'll do is we'll take this vector. This will be like multiplying it by 1. And then on this side, this is like multiplying it by -1. And then we will do 2 extensions in these 2 different directions for each one of the points. And in P5, if you want to draw a shell like this, where you have an inside and outside, inside, outside, you can still use begin shape, but there's this extra thing you can pass in, go begin shape, triangle strip. And what this will do is if you put them in this order, so this is like the first one, second point, third point, fourth point. So you always go inside, outside, inside, outside, inside, outside. Then P5 will draw this whole shell for you. So that's going to be our strategy. So one thing that we'll notice here is just right now I've got 3 of these directions, but I've got 4 points, but I still need to extend this last one too. So what I think we're going to do is just copy and paste this direction and like reuse it for this last point, because it doesn't really matter what it is, and this is probably good enough. So let's try coding this up. So I'm going to get rid of this line code because we're going to go back to using begin shape, end shape. So the first thing we want to do is get these directions here, the red ones. In math speak, these are called tangents. If something is tangent to a curve, it's going in the same direction as the curve. And these pink ones that are perpendicular are called normals. I don't really know why it's called a normal, but that's what it's called. If you have to Google it, those are the words to Google. So let's make an array of tangents first. So I'm going to loop over each consecutive pair of points. And I'm going to get the previous and the next one like we were doing before. And then the tangent at that point is going to be the next point. Oh, got a typo in here. And then I'm going to subtract from it the previous point. And then I mentioned before at the end, we're going to just copy and paste the last one. So I'm going to do that over here too. So that will give us our directions. I think I'm also going to call .normalize on them. So what that does is it will keep the same direction, but it will change the length so that it's of length 1. So if this was really long before, it'll shrink it to length 1. If it was really short, it'll bump it back out to length 1. So that way we kind of just have a direction without a length. And now to get the normals, we're going to take all the tangents, and we're going to, for each one, going to rotate it 90 degrees. So I've used degrees here, so I'm going to just change the angle mode in P5 from radians to degrees. And okay, so now we've got the normals. So now let's draw our shell. So we're going to use our triangle strip mode so we can loop over the inside and outside of a point. All right, so now we've got a point and a thickness inside each one. So for each point, we got to do inside and outside. So I'm going to loop over those two things. And I mentioned that the inside is going to have this -1 multiplier and the outside is going to have this 1 multiplier. So that's what we'll loop over. And then based on that side, we're going to extend in the direction of the normal. So let's get the normal. So I'm going to need an index here. In order to get the index, I'm going to add .entries, which gives us key value pairs. So it's like, instead of just the objects that we're looping over now, we're looping over a combination of their index and the object. So, okay, so now we've got the normal. And let's put a vertex. So instead of just doing it on the position of the point in the middle, we're going to add the normal times the side times the thickness divided by 2, because we're extending in 2 directions here. So if I want this whole thing to be the thickness, then I'm only going to go halfway on each side. And then we're going to do the same for the y. And let's see how that looks. Okay, so a few things are going on here. The first one, you can see that it's definitely making the triangles for us. And that's because we're actually still visualizing all of the lines of the shell. We don't actually want that anymore. So I'm going to take off this stroke and I'm going to say no stroke. And we've actually got a full shape to fill. So we can now rely on the fill style instead of the stroke style. The other thing, first let's test that. It doesn't look like we're as wavy as before. And I think that is because I've changed the angle mode to degrees. And over here, I'm using a sine function, which was radians before. So I'm just gonna set the angle mode in this function to radians. And see if we get the same look as before. Okay, there we go. So now this looks a lot smoother. Next step, we'll probably want to grab actual interesting thicknesses instead of just this like arbitrary sine wave. So maybe what I'll try to do is grab the thickness based on how far the mouse moved. So if between mouse points it moves really far, it's like I'm moving the mouse really quickly. In that case, I'm going to make it thicker. So let me take out this thickness, and I'm just going to say we want the distance between the previous mouse and the current mouse point. So the previous mouse point is p mouse x and p mouse y, two special variables again, and the distance from that to the target point. So this kind of works. If I go fast, I get a much thicker stroke, but it's still really wobbly. This actually kind of looks cool. So maybe if this is a look that you like, you can just stop right here. But I think what's going on is it depends a lot on like how the browser samples your mouse. So when the browser checks for the mouse position, sometimes the amount of time between the last check and the current one is like a little bit different. So the distance that it looks like it's traveled has changed a bit. So what I think we can do is instead of directly taking this thickness, we can do the same lerp trick where we kind of just blend between the previous one and the next one in order to smooth it out. So I'm going to call this the target thickness. Oops. And let's get the last thickness. That's basically the same as this, but instead of the point property, it'll be dot thickness. And then we'll do the same kind of blending with lerp from last thickness to target thickness. And I'm going to also use 0.1 to see how that looks. All right, this is looking pretty good. I like that smoothness and that thickness. One little visual thing that I don't know how well it's captured in the video, but if I zoom in, maybe, we've got these little like slightly lighter areas in between the triangles. And that is because how P5 renders this and how all 2D JS canvases work is it kind of anti-aliases each shape individually. So it tries to smooth the edge on one triangle before it draws the next triangle. And sometimes those anti-aliased edges don't perfectly add up to one. It kind of depends a lot on the anti-aliasing algorithm. But a little trick up our sleeves is we can switch to WebGL mode and it does all of its anti-aliasing all at once. And we'll get rid of this issue. So I'll turn on WebGL and turn on WebGL anti-aliasing. And oh, right. So there's an offset right now. That is because in 2D mode, the top left is 0, 0, but in WebGL mode, the middle is 0, 0. So if you ever start something in 2D and then switch to WebGL, you'll probably end up with a line like this at the start of your draw, which translates negative width over 2 and negative height over 2 to just like bring it from the middle back to the top left. And now we've got basically the same thing as before, but with much smoother lines with no little seams in between the vertices. So this is looking pretty good. We've got a good solid stroke, but we can still push this further. And so I mentioned I work on WebGL. There's a lot of things that you can do in WebGL that are kind of unique to WebGL mode, but are a little bit less well known just because it's a less common mode to work in. So I'm going to take this opportunity of being in WebGL mode anyway to show you some of the things that WebGL can uniquely do. The first one is in WebGL, you can change the color between vertices and it will smoothly blend between them. In 2D mode, kind of like how when we were changing up the stroke weight, it could only keep one stroke weight per line. In WebGL, we don't have that restriction for color as well, which 2D mode has. So instead of doing the fill out here at the top, I can do the fill inside the loop for each point. So maybe I'll keep it black, but I'll change up the opacity. So maybe like when the stroke is really thin, I'm also going to make it a little bit less opaque. So to do that, I'm going to map the thickness from, let's say, like 6 to 12. And I'm going to convert from that to, let's say, like 50 to 255. So all of these color channels are going to go from 0 to 255. So 50 is like 50 over 255. That's around 20% opacity up to full opacity. So now if I draw this, so if I make a smooth line, it gets lighter. And maybe I can actually bring this up so it's more noticeable. So you can imagine doing this with color too. So that's one cool feature of WebGL. There's some more we can do too. There's this thing called texture coordinates. So this is a picture of me. It's just kind of what I have lying around. Everything in my downloads folder ends up in test graphics whenever I'm working on stuff. So anyway, we have in our vertex calls, we have an X and a Y. Technically, there's also a Z, but even though this is about WebGL now, we're never going to have anything but 0 in Z. You can also add 2 more coordinates, which will correspond to a point on an image. So if I say that like at this vertex, I want to correspond to this point on the image, it's going to pin that point of the image to that vertex. So then it can be used to distort an image or like form fit an image to any shape that you draw. So I've got that same picture just kind of like lying around secretly on my desktop here. So let's upload that and bring it in to work with. Okay. Let's import the image. In P5, we've got our preload function. And anything that you load in here is going to finish loading before it runs the rest of your sketch. So I'm going to say image equals load image. And I just called it dave.jpg. Great. So now what we're going to do is instead of setting a fill anywhere, I'm just going to comment that out. Right at the start, I'm going to use texture and pass in that image. And I'm also going to set, before I put in some coordinates here for the image, texture mode normal. So by default, if you supply these extra coordinates, it's just like pixels on this image. But if you set the texture mode to normal, then the coordinates you put in go from 0 to 1. And what that means is you can swap out a different image that's a different size, and it will still work because you're just using like a fraction of the width and a fraction of the height as your units. So it's just like easier to test different things without having to also update your code, which is why I like working with normal mode. Okay, so we're going to put in 2 things. We're going to put in the X and the Y of the image. So the X value, I'm going to say whether or not we're like on the inside or the outside of the stroke. So I'm going to map the side from -1 to 1 to the range 0 to 1. And for the Y, that's going to be how far along the stroke we are. So I'm going to map the index from 0 to stroke dot length to the range of 0 to 1. So now if we draw, we have the image stretched all over the stroke. And just to like prove that this is in fact the image, let's just make this thickness a lot bigger, multiply it by 10. Whoa. Oh, right. That's because this is the lerp thickness. I'm just gonna put the target thickness times 10. So this is in fact the image. You can see as I expand the width that like the wobbliness in the thickness is still there. Like there's a little bit of like weird line like visibleness here. And you can also see as the image bends, there's like some artifacts because of that. So there's definitely more smoothing that you could do with the stroke width if you're going to make really thick strokes. Like we could try averaging the normals. So just like for each one, adding the previous one and the next one, then dividing by 3 or something, just to like make it a little bit more smooth. But that's fine. I'm gonna bring this stroke thickness back to the way it was before, and we'll get rid of this texture in a sec. So you can imagine using, instead of this random picture of me, you could use like a brushy texture instead. Kind of like import different images like you would like a brush in Photoshop. They've got different settings. But it would be kind of cool if you could use code to make that texture and have it be dynamic maybe instead of a fixed image. Because right now it still looks like I'm just stretching an image across the stroke. So it turns out there's a thing for this, and it's called a shader. You might have heard of these online, and they sound pretty scary, and they maybe sound scary because when you see shaders online, they are stuff like this. So here's a shader from Inigo Quiles, who makes these like really unreal shaders with like crazy like environment and like character rendering. So I mean, this looks great, but this looks pretty imposing. And here's one from Evil, who does some great demo scene streams where you can just like watch them write stuff like this. This has got some pretty interesting geometry in it, some intricate wavy 3D curves. So anyway, this is what I think the most visible look of shaders is, but like shaders don't have to be this. Shaders are actually just programs that do some very specific things. They let you change the position of vertices of a shape and change the color within that shape. And kind of the thing that makes shaders special is that they run on your GPU instead of on your CPU. So it's like our computers have this special hardware that is made for doing a bunch of stuff in parallel. So anything that you could do with shaders, you could also do with not shaders. So like we've already been adjusting vertices. We don't need a shader to do that, but we're kind of just doing them one at a time in a loop. Whereas if you do it in a shader, it's affecting all the vertices at the same time, so it can be a lot faster. And even same for coloring the pixels. In P5, you have access to the pixels array, which you could just loop over and edit pixels that way. But a shader just lets you do all of them at the same time in parallel. So it's a lot easier to make animations where you do these like per pixel calculations, whereas it would run pretty slowly if you did this without using the GPU at all. So WebGL gives you 2 spots corresponding to those 2 different things. So you always start off with your vertices as vertices of triangles in JavaScript. And then the first spot where you can write one of these programs is the vertex shader, which runs on every vertex of every triangle. And initially, this is going to be really simple. Like the bare bones vertex shader just applies the camera transform. And that's like, we have this like translate call. That's just doing stuff like this. So whenever you have a translate, it applies the translate to the raw X and Y points that you've passed in. And that's all we're going to start with for now for that. And then the second spot is the fragment shader. And that's the one where once it's positioned all of the triangles on the screen, it runs this program for every pixel in every triangle, and then you can come up with a color. So that's what we're going to go ahead and do. Unfortunately, WebGL is a little bit less accessible than other types of like 2D canvas APIs because it gives you a lot more flexibility, but because of all that flexibility, there's a lot more boilerplate. So I am going to copy and paste that boilerplate. Feel free to do the same. There's no shame in copying and pasting this stuff. I never write it from scratch. And also in the slides and also in the website that I linked with all these resources, it also has the stuff to copy and paste from. So I'm going to make our vertex shader, paste that in, and make a fragment shader and paste that in too. And if you use the file extensions .vert and .frag in the P5 editor, it will give you this nice code highlighting. Oh, actually, let me just drop that link in for you in chat. There you go. All right, so I'm gonna get rid of this image and instead load a shader. I'm gonna call it, say, stroke shader. And you can use load shader for that. And we're going to pass in the file paths to those 2 bits of source code. So shader.vert and shader.frag. All right. And I'm going to now take out this image thing. I'm going to keep the texture mode normal in here, just because we're still using the same range. And I'll put the fill back in for now. So, and where I had the texture before, I'm going to use this shader call. So now if I run this, it should look exactly the same as before. And that is because we're using some like boilerplate code that will kind of just do exactly what the default does. But to prove that it's actually doing something, I'm going to edit this fragment shader, which is the one that does the pixel colors. And I'm going to edit it. The syntax is a little bit different. It's kind of like based on C, if you've used any of that. So the way that this works is we've got this magic variable called GL frag color. And whenever we set that, that's going to be what the pixel color is. And we can set it to a vec4, which is a special data type. It just means it's got 4 values in one thing. And that corresponds to the red, green, blue, and alpha channels. And in the shader, all those are in a 0 to 1 range. So if I want to make this red, I'll do like 1, 0, 0, 1. Unfortunately, because it's based on C, I have to add like a dot after each number to let it know that it's a floating point number and not an integer. Otherwise, it's going to complain. So if you see me adding a dot, that's why. It's kind of like saying 1.0, but the 0 is extra. So now if I draw this, wow, it's red. So I'm going to put this back to how it was before. And instead, we will use some other code to change up the style here. So I'm thinking maybe what we'll do is we'll try to make a rough texture. And if I were to try to make a kind of rough texture in 2D mode, I'd probably reach for P5's noise function. So noise is like something that looks kind of like this. So if this is your input and this axis is the output of noise based on the input, you kind of get a graph that's like sort of random, but unlike if I were to use like an actual random number, which is literally just random points. So if you zoom in, it's still just scattershot points that aren't connected or anything. This is smooth. So that means we can sort of spread it out or collapse it as much as we want. So unfortunately in shader code, it does not give you a noise function. But thankfully, Patricio, who is the author of the Book of Shaders, which is a great resource if you want to see a lot more techniques that you can use in shaders, has provided a gist on GitHub with some noise functions for a shader. And I'm just going to shamelessly copy and paste those in so that we can use them. So now I've got some noise functions. So what I'm going to do is I'm just going to multiply the color that we're passing in with some opacity. And let's define what that is. To start off with, maybe I'm just going to use raw noise without anything else. So I have to pass in an input to the noise like X here, but we have like a 2D noise function that takes in a vec2, which is just a 2D vector. So I'm going to pass in the texture coordinate, which you'll remember is what we were using to define where on an image we should be. So it's kind of like we're just treating the noise like an image. So now if I run this and I draw, so it's definitely changed things, but it doesn't really look noisy. but that is probably because our texture coordinate is from like 0 to 1. So instead of looking at this whole graph here, we're kind of just looking at like this tiny little slice of the graph. So that's why it's very smooth. So if I want to expand it to be this whole range, then what I'll have to do is probably just multiply this by something times maybe 10. Great. So now we've got something here. In this axis, it definitely looks like there's more stuff going on, but it still looks really stretched in this axis. And that's because this is also from the range 0 to 1. But now that we're not using an image anymore, these texture coordinates, they're kind of just numbers. They can be anything. So they don't actually have to be between 0 and 1. Part of the reason why it also looks like it's sliding as I keep dragging is because it's like stretching the 0 to 1 out the whole way. But if I just use I here, then that number isn't going to change at each point. So it's going to look like it's staying in place. Cool. So now we've got a noise texture. This looks like static on TV. Maybe I'm going to try doing a threshold on this. So it's like, instead of punching out holes everywhere, I'm just going to punch out a few holes here and there. So to do that, I'm going to use a function in GLSL called smooth step. And it's kind of like map in P5, except it always maps to a 0 to 1 range. So we just have to give it the input. So I'm going to try mapping from, let's say, 0 to 0.2. And so I'm mapping this value from the range 0 to 0.2 and putting that into the range of 0 to 1. So now if I draw, I have punched some holes out. So this looks like more like what I was hoping for. But we can also make this be relative to the thickness here. So maybe I want it like, as it gets more transparent, I also want it to poke out more holes. And we have access to this as well. That's the V vertex color thing here. So maybe instead of going from like 0 to 0.2, I'm going to go from like the vertex colors alpha channel, which is the .A, and .A minus 0.2. So I'm just kind of like, this would go from 0 to 1, but I'm just mapping from like a small range of like size 0.2. And this looks like it's doing the opposite of what I want. So I'm just going to do a 1 minus at the start. So now it gets rougher as it gets thinner. And then if I move the mouse a lot, it looks reasonably thick. So this is pretty good. This is something I would be able to use to get some interesting lines for sure. So I'm going to actually save just because we've made a lot of progress. It's always good to save, remember. And the next thing that we'll do is maybe take a look at this vertex shader. So this is affecting the position. Something that would have been kind of hard to do in 2D mode is animate these lines, but now we have a way to animate it. So maybe I'm just going to make the lines wiggle. Always good when you make stuff wiggle. I want it to wiggle based on time, so I need to give the shader access to time. So let's do that. Actually, before I jump in, let me just like take a look at what this boilerplate does and explain it a bit. GL position, that's the magic variable we have to set in order to tell WebGL where the pixel goes. And what we're doing to get the position is we're just multiplying, this is like the camera transform matrix by the input position that came from JavaScript. So this is how we're applying the transform and then setting the position. And then this bit here is just how you would pass extra information on to the fragment shader. So in this case, we got this color and texture coordinate input from JavaScript, and the vertex shader doesn't need it yet, but the fragment shader does. So we just send it out with these things called varying variables. But anyway, we want to also get the time as an input. So if you want to add a new input to a shader, there's a type of variable called a uniform variable, which just means it doesn't change per vertex. It's just like a constant. So I'm going to call it a float time. And to pass something from JavaScript to a shader via uniform, you can just go after you've set the shader, you can say stroke shader.set uniform, and it's called time. And I'm going to set it to the milliseconds that have gone by so far. So let's now make use of that. So we've got this position, which right now is like directly from JavaScript. I'm going to make my own position variable. And it's going to be equal to the stuff that we started with, but then we'll update it a bit. And we'll add to it with, let's say, like, we'll move it around like 20 pixels based on a sine function of the time. So this is in milliseconds. There's a lot of milliseconds per second. There's 1,000 of them, in fact. So I'm going to maybe like divide this by something so it gets smaller. And I'll just do the same for, this is the X coordinate, this is the Y coordinate. And then I'm just going to leave Z 0 because we're just doing 2D stuff in WebGL. And so this is just going to move the same amount in X and Y, but let's see how it looks. Okay, so it's moving kind of slowly. Let's take out some of these zeros. Okay, it's definitely moving. It's moving directly in this axis because I've given it the same value for X as Y. So maybe I'll just add like a 0.5 or something just to throw it off a little bit. So that should like change the angle. It changed the angle a little bit. The other thing is it's still moving the whole thing as one piece because this is running for every vertex, but we're giving it the same value for every vertex. So if we want to change over the course of the stroke, we have to like give it some input that actually changes. And we can maybe use this texture coordinate for that. So we know that like along the length of the stroke, it's gonna go from 0, 1, 2, 3, 4, 5, all the way up to like the length of the points in the stroke. So maybe I will just add something in here. So we'll say like a text chord dot y is the length one. And then I'll just like add that in maybe. So it's just a different offset for each vertex. All right, so that's definitely different per vertex now. This is moving pretty high frequency. I'm gonna maybe divide this or like multiply it by something small in order to make the waves spread out more. Okay, this is looking pretty good. This is actually kind of intense now. I'm gonna change the size to 10 so 20. Okay, I think this is pretty good. So now I can write something like hello. And we have our whole stroke wiggling. So this is something that you can do with WebGL that would have been pretty unthinkable with 2D mode, like still possible, but I want to shed some light on all of the possibilities that you can get if you just jump into this shader programming world. And again, you don't have to do 3D in order to do it. There's nothing 3D here, all 2D stuff. So I am going to wrap up the talk at this point. We've only got 5 minutes left anyway. And maybe just like leave you with a few different things that you could try out if you wanted to do some different things. So remember I mentioned that this like texture coordinate thing in a shader, it doesn't like have to correspond to an image. It's just numbers. So you could put anything you want in there. Like you could put a direction vector in there if you want to make your texture and your shader correspond to the direction that it's going. So like if you imagine like a brush, as you rotate the brush, the bristles kind of like move in the direction of the stroke. You can do something like that way. Something else you can do, going back to the texture example, you can use in P5, there's a thing called create graphics, which lets you make kind of like another P5 canvas that you can draw to and then use it as an image. So you could make a P5 graphics and use that as a texture. So if you wanted to like draw some text and maybe have the text scroll along the stroke, that would probably be a way to approach it. That would work pretty well. And again, there is this whole world of 3D that you can always jump into if you want to. So along the way, we ran into a few little bugs here and there. I went through them pretty quickly because I have written this code before, not necessarily live, but I have written it before. And that is on open processing if you want to go through it. But if you are writing stuff without a reference like this and without the practice and get stuck, there is a P5 Discord that you can ask some questions in. And there's a lot of people here who help answer the questions. And there's also normally me, this one is me. I hang out in here a lot and maybe I can help fix your problem. So that's always an option that you have at your disposal if you get stuck. Anyway, thank you all for your time. Thank you for listening and let me know if you have any questions.